Hello to all of my physics-loving students. I am preparing a new video today. This will be a review on motion in one dimension, significant figures, motion in two dimensions. And this will be different in that I'm trying to add a video of myself teaching you. Going forward, I hope to do this. So here, let's get into it. The topics for the day, as I mentioned, are going to be measurements, in which we will look at the different units that are used. We will look at vectors. We'll be looking at motion in one dimension and also motion in two dimensions. So that is what this is going to be about. Let's jump straight into it. First of all, there are 7 basic units in the International System of Units, but we only use 4 of them in the first semester. And these 4 are the meter, the kilogram, and the second. The meter is the unit of length. Kilogram is the unit of mass. And second is, of course, the unit of time. So these are the main units that we use. And when we do thermal physics, we will also use Kelvin as the unit of temperature. And many times problems in physics will be given in other units, but you need to know how to convert from one system into another. And although there are many prefixes, the most important prefixes are milli, that stands for 10 to the negative 3, micro for 10 to the negative 6, centi for 10 to the negative 2, kilo. Now that's on the higher side. Kilo is 1,000, so it's 10 to the 3. Mega is exactly the opposite of micro, which is 10 to the 6. So mega is 10 to the 6. As an example, 1 millimeter is 10 to the negative 3 meter. 1 centimeter is 10 to the negative 2 meters. And again, a kilogram would be 1,000 grams, or 10 to the power 3 grams. The unit of resistance is ohm, and mega ohm would mean 10 to the power 6 ohms, or a million ohms. So that's about the units. Now when we come to significant figures, I'm just going to quickly refresh your memories and tell you that it's very important to write the final answer in the proper number of significant figures. And the best way to do it is converting a number into its scientific notation. So if you have 0.00475, in the scientific notation it becomes 4.75 times 10 to the negative 3, which clearly shows that there are 3 significant figures, 1, 2, and 3. Now there are many rules to find the number of significant figures in the answer, but basically if it is, okay, here I've given another example. Before I go to the rules, it's 36,400 written in the scientific notation is 3.64 times 10 to the 4. So there are 3 significant figures. Now when you write it in the scientific notation, you don't have to hassle with the number of zeros, whether it's leading zeros or lagging zeros, and all those confusing rules. Now if you are multiplying 2 numbers, as given in this example, the product should have the least number of significant figures. which in this case is 2. So the answer is 100. But when you're adding two numbers, be very careful that the significant figure rule in this case is the least number of decimal digits. So 1.2 has only one decimal place, therefore the answer should only have one decimal place. So that is the difference. So when you multiply and divide, you have one rule, which is for multiplication or division. You look at the lowest number of significant figures and the answer should have the lowest number of significant figures. But when you add or subtract, you're not going to look at the lowest number of significant figures, but you look at the lowest number of decimal places. So in this example, there was one decimal place. That was the lowest because there was 2 here. So that's why the answer will have only one decimal place. Now, one word about dimensions. I'm just giving you an example. This is the van der Waals equation for gases. And let me explain the terms. You have P, which is pressure, you have volume, and then you have two constants A and B. On the right hand side, you have the universal gas constant and the absolute temperature. We don't have to worry about that, because in this question, I'm going to ask you to find out the dimensions of A and that of B. Now, the idea is that if two quantities are added together, both of them must have the same dimensions. So since A by V squared is added to P, A by volume squared should have the same dimension as that of P. And once again, since B is subtracted from volume, the dimension of B should be the same as that of volume. So let's take the first one and try to find the dimension of A. All right, so we find the dimensions of A and B. And like I said, P and A by V squared should have the same dimension. Now, P is pressure. Pressure is force by area. Force is mass times acceleration. And so the dimensions of force are mass, and then acceleration is Lt raised to minus 2. And area is, of course, L squared, which goes to the top, becomes L raised to minus 2. And therefore you have L to the power 1 and L raised to minus 2, so that's going to be L raised to minus 1, and then T raised to minus 2. Therefore, A by V squared should also have the same dimension, which means when you take this to the right side, you get the dimension of A, and that's volume squared, and that's L cube whole squared. So you get the final dimension as L to the power 5, because this is L to 6, and then 6 and minus 1 is 5, so you get M L raised to 5 T raised to minus 2. Hope that makes sense. And then to find the dimension of B is pretty simple. It should have the same dimension as that of volume, which is L cubed. So V and B have the same dimension, and that should be L cubed. So that's one word about dimensions. And it's pretty useful in finding if an equation is correct or it's wrong. And one word about vectors. Vectors are very important, and this is, remember, it's a fast review. And I'm just going to tell you that there are many ways of adding vectors, but we're going to be using the resolution method. So that means if you have to add two vectors, you will resolve them into their components. As you can see, this vector has been resolved into its x component and into its y. I'm going to do the same for the other one. That's the x and the y. I know the y could have been a little better than that. So if these angles are given as theta, and the vector is a, the other one is b, and this angle is alpha, the horizontal component is going to be a cosine theta, and then the vertical is a sine theta. Here it's b cos alpha and b sine alpha. Once you get the x components, add the x components together, do the same with the y, add them together. That is what is shown here. So this would be a cosine theta, or rather a cos theta plus b cos alpha. And this is a sine theta plus b sine alpha. So the final sum is given by this vector, which is a plus b. So that's a cos theta plus b cos alpha. This is a sine theta plus b sine alpha. Let me call them p and q. So to find the magnitude of the vector or the resultant, which is the absolute value, you just square both p and q, add them, take the square root. And to find the direction of a plus b with the positive x-axis, you can see that the angle is beta. And so tan beta is going to be the opposite side by the adjacent side, which is q by p. So this is how you add vectors. And to subtract vectors, just take the opposite of the vector that you're going to subtract and add it to the first one, because a minus b is nothing but a plus the negative of b. So since this is a review, I'm going fast. Now we got to look at kinematics, beginning with the motion in one dimension. I'm just going to give you the equations, and you got to be careful about how and where you use the equations. If you are absolutely sure that an object is moving at constant velocity, that's when you use this equation to find its displacement. Displacement is velocity multiplied by time, and that is from v is equal to dx by dt. Now, if you have an object that moves with constant acceleration, then there are several equations that can be used. First of all, you can find the displacement by using the average velocity multiplied with the time. And the average velocity is, of course, the sum of the initial and the final, divided by 2, then multiplied by time. So that is one equation. The second one is a very useful one. We have used calculus to derive that. It's delta x is v naught t plus 1/2 at squared. Where you know that v naught is the initial velocity, a is the acceleration, and t is the time. And then you have vf is equal to v naught plus a delta t, which comes directly from the definition of acceleration. And of course you have vf squared is v naught squared plus 2a delta x. Now if you look at each one of these equations, you see that this equation does not have final velocity in it. First one does